Hey there, in this video we're talking about function templates in C++ programming, and this covers sections 16.2 to 16.3 in the Gaddis textbook. So function templates. The basic idea here is, let's say you're in a situation where you're making a lot of overloaded functions that more or less do the same job with different types of data. Well, what you could do instead is you can make just one function that does that same job but is able to accept any type of data coming in via the parameters. That's called a function template. So that's another technique that's going to allow you to avoid repetitive typing and repetitive code maintenance. Instead of a whole bunch of functions, you'll just have one single function do that job in the form of a function template. Okay, so before we get into the details of that, let's talk about the general scope of this part of the course. So we're in the last 4 or 5 chapters of the Gaddis textbook now, and where I teach at CUNY Kingsborough, this part of the course will represent the last couple weeks in our first year programming sequence. So what is this part of the course about? Now, number one, we're getting more practice at object-oriented programming. So if that's relatively new for us, it's a good idea to get more practice reading class definitions, being able to make objects, confirming that we know how to use them, being able to test them, things like that. So item number one, getting more practice with object-oriented programming. Number two is we're giving you a little bit of a preview to probably what your next computer science course will be. You'll probably take a course called Data Structures. It's pretty common for the third course in the major. Again, where I teach at CUNY Kingsborough, that's our CS 3700 course, is the next C++ programming course called Data Structures. And the theme there is we dig into a whole lot of other strategies for storing data, a whole lot of other clever possible strategies for storing large amounts of data. So the primary theme of this part of the course, this preview that's happening now, is thinking about the possibilities of abstract data types, or ADTs for short. So we've been making new data types for a while now, using structs, using classes to make new data types in C++. And the idea of an abstract data type is a data type that only specifies to the application programmer the bare minimum of what they need in order to use it. So an abstract data type should specify the values that can be accepted into the object, parameters coming into the public functions like the setters or the constructor, okay, what values can be sent into the object, and what operations are possible on the object type. Can you take this type of object, can you add them, can you subtract them, can you multiply them, can you print them? Sometimes yes, sometimes no, depending on the type of data. And of course, those operations are really the public functions of the data type. So you'll have to specify those things, what can come into the data type, what functions, what operations can happen on them. But the user of the abstract data type, which is to say the application programmer, does not need to know about the implementation details of how the data type stores its data or does its work. And what we'll see in these last couple of videos for the end of the class here, we'll see various implementation strategies that we could use to store a whole lot of data inside an object. And some will be better for certain purposes, and others will be better for other different purposes. So those implementation strategies will be hidden to the application programmer. And on the one hand, the class programmer can pick from this menu of options to store data, but the application programmer will absolutely not know about any of that stuff. It'll be invisible to them. They won't need to worry about that, and they won't even know which strategy the class programmer used. And that difference is what we mean by abstraction. All the details about how the data is actually being stored and manipulated are being abstracted away, and the application programmer won't know, doesn't need to know about them, and that's great. So that again is another technique for letting your teams build out larger systems much more rapidly. Now, one great way of setting this up is to use an abstract base class that we talked about right at the end of chapter 15, if you remember that, using pure virtual functions. And so maybe your abstract base class at the top of a class hierarchy, maybe it doesn't even define any data at all. It just specifies the basic public functions for what this abstract data type needs to do. And then the class programmer can build out a whole bunch of inherited child classes that use the different strategies that we'll talk about in this part of the course. And of course, the application programmer can make a function that takes a reference to that kind of abstract base class. Even if you can't literally instantiate one of those things, you can make a function that receives a reference to one of those things, and then you can pass in any one of the different child classes using any of the different data storage strategies. Okay, so using an abstract base class, a great way to set up abstract data types. We'll probably see that over and over again in this part of the course. So hopefully that's a pretty good idea. This last part of the course, abstract data types, the primary topic of a data structures course, which will probably be your third course in computer science. So I like that we're getting a little preview to the next course, but also getting more practice at object-oriented programming. Okay, so function templates. Again, making things that are abstract, that are taking away the details and being able to manage a whole bunch of different types of data. So our first step down this path is function templates today. And what a function template is a pattern for a function that can work with abstract data types. That can receive a data type and you don't even know what's in it. And the function can still work anyway. So when you write one of these things, what we'll see is that the parameters coming into the function, the types will be left looking like they are variables. So in addition to the actual variables, to my mind, now that you're not actually going to write int, float, char, bool, string for the types, the type itself will look like it's a variable. And the function will be able to work on any one of those things. And what happens is that when you call a function like that, one of these function templates, the compiler is going to spot that, and on the fly, while it's compiling, it's going to automatically generate code for that version of the function call that works with that particular type of data. So, you can kind of think about what happened in chapter 15. We wrote a function that handled multiple child classes. Again, it took a reference, took a pointer to an abstract base class, to a base class in a class hierarchy, and then that function could actually work with a number of different data types as long as they were all in the same class hierarchy. Now this right here might actually be a little bit better because the incoming types don't even need to be in a class hierarchy. It should actually be able to work on anything as long as the operations that you need to work with are defined. So this might actually be an even better idea than the idea from chapter 15. Okay, so here's what this looks like. When you're setting up a function template, you're going to have a template prefix. Okay, so this template prefix is part of the prototype, right? Sometimes I just write the whole prototype in just one line. For space purposes, you're seeing it on 2 lines here. So this template prefix says, template's a keyword in C++, says here comes a function template, and then it gives angle brackets, and you have to say class there, and this capital T is there it is. It's called a generic data type, and again, to my mind, it's like a variable for a type. So where you'd normally see int or float or char here, you're just going to see capital T instead, and it stands for whatever type you would like to pass into this function. Okay, so class T here. Now, a little side note, this is not a preprocessor directive. This is not a pound include statement. It doesn't just happen once at the top of your code file, like with pound include. This is part of the function prototype, and every single function template has to have that separately, okay, as part of the function prototype. So here is the rest of the function prototype. You see the return value here in this example is type T, not int or char or string. Type T could be any one of those things, frankly. The name of this function is called square, and to my mind, clearly squaring is when you take a value, multiply it by itself twice. Okay, great. And then the incoming parameter here is type T. Could be any one of those things. The name we're giving that parameter is num. And as you can see here for this very simple example here, just one line of code here, you take num times num, which is of course what I expect to see for a squaring operation, return that, and presumably if you multiply 2 things of type T, you get a type T result to finish with, and that is what we return, a type T thing. So you see that type parameter here showing up for the return value in this particular case, for the incoming parameter in this particular case. And that's a pretty good example of a function template. So when you call this, right, when we write this, this function doesn't know what type you might possibly send into it. Could be integer, could be a double, could be a character, could be a string. The only thing that this function knows is it's something that you're able to multiply. Okay, so the fact that we use the multiplying asterisk in this code means that the incoming type has got to be able to multiply by itself. So you might think about that. Can I multiply two integers? Yes. Can I multiply two characters? Well, yes, actually, because characters are a type of integer. Can I multiply two strings? Well, no, because the multiplying asterisk is not overloaded for the C++ string class. So actually, this function will not work for strings because you didn't define the multiplying asterisk. But anything that you do have multiplication defined for, this function will be able to accept it. So at some point, when you call this square function, if you happen to pass in an integer, the compiler is going to spot that and say, hey, I need a version of this square function that works on integers. And it's going to create automatically and compile a version of that function like this. Returns an integer called square, receives an integer, multiplies those two things. But if you call this function and pass in a double, the compiler is going to spot that and say, apparently I need a version of this that works on doubles. So I'm going to automatically create this code, automatically compile it for you, and now I have a version of square that returns a double, accepts a double, multiplies two of those things. Again, that's all automatic. You're not literally going to see it in the code. It's just put in the object file as soon as you actually call this square function with one of those types. And that's the nice thing about a function template. Okay, so just to kind of emphasize that here, if I make an integer called iValue, set it to 3, and I make a double called dval, set it to 2.5, and then I have a couple lines of code. This right here is what the compiler picks up on and knows I need to compile a version of square that receives integers. And this last line here is the compiler sees that and goes, you're passing in a double to this. Apparently, I need to compile a version of square that receives doubles. And if you run this code, of course, the first version multiplies two integers. 3 times 3 gives you 9. Hands back that integer for a return value. And this last statement here does 2.5 times 2.5 and returns the double value, 6.25, following along whatever you passed into it. Great. Now, we could also, so obviously we can pass in an integer, we can pass in a double, we can pass in a character. In theory, it could be other objects. Maybe we could pass in a feet inches object, right? Again, in order for that to work, you'd have to overload the multiplying asterisk on feet inches objects, like the book already did add and subtract and increment and stuff like that. There is a programming challenge in chapter 14 that asks us to overload the multiplying operator for feet inches objects. And if we did that, if that made sense and we did that, then you can even pass a feet inches object into this function, and that'll work just like that. And again, the compiler would spot that and say, I guess I have to compile a version of square that works on feet inches objects, multiplies them, and passes back a feet inches object. And that'll totally work, as long as you've overloaded the multiplying operator. Okay, a couple other notes on that. Now, that example just used one single class type there, one single abstract data type. You can have more than that. So if you need more different types coming into your function, then your class prefix, your template prefix here, can specify multiple incoming classes. So here I've got T1 and T2. Now, I will point out that as far as the naming of the abstract types, the book is in the habit of using just capital T, like one single letter for that. That's pretty common, so feel free to just use capital T or T1, T2 for your abstract data types. Some other people will use more formal names, like they'll say, input type or data type, capitalized for the names of their abstract types, and you can do that too. But this is what the book does here. This is fine. This is pretty common, honestly. So an example here of using two different types for the parameter values. So you have a template here, again, part of the prototype. You've got a class called T1. You've got a class of type T2, whatever that is. This here is a function called MPG, presumably to compute miles per gallon of gas usage, I guess. And so the miles will have its own type called T1. The incoming gallons parameter will possibly have a different type, T2. They could be the same, they could be different. And obviously, to compute miles per gallon, you have to divide them. And this right here apparently is deciding to pass back a double. So these two types, whatever they are, have to support the division operator in this case and have to be returning a double when you get done with that. And granted that, you could pass in any two types of parameters as long as they know how to divide by each other. And you can do that. You can have 3 or 4 or 5 different types, of course. A couple other notes about that. Now, all of the data types specified in that template prefix must actually be used in the function, must be used in the template definition. So for example, something you cannot do with the postfix increment operator from chapter 14, there's this dummy integer being passed in that doesn't actually get used for anything. We could not possibly do that with a function template. You actually have to use all of the specified types. Second thing here is function calls actually do have to pass in parameters for all the types specified in the template prefix. So for example, you cannot use default arguments here, right? Default arguments in a function call automatically fill something in. But for function templates, it needs to see the type that you're intending to use. So you absolutely cannot leave parts of one of these function calls blank, because the compiler needs to see what type you're intending to use and then create code for that type. So you will have to explicitly put down every single parameter in one of these function calls. You can declare local variables of the generic types. So like if internally I need a temporary variable for like a swap or a return value, I can locally declare a type T, result, do some math on it, and then return that at the end. You can totally do that. So a lot of flexibility here. Now, some other notes about the specific ways that function templates are implemented. So item number 1, a function template is a pattern. It's just describing to the compiler how you're going to create one of these functions. It's not actually really code, but just directions to the compiler for when it needs to automatically create code. A function template by itself doesn't use any memory at all. No actual code is generated until the function named in the template is called. So for example, if you had a .cpp source code file and all it had was function templates, and you go to compile that to make a .o object file, what you'd find is that .o file would literally just be empty. There wouldn't be anything there at all. A function template all by itself can't be compiled into machine code, right? What it takes is the template plus a function call to it. And that's the trigger for the compiler to spot that and then create the code that you're looking for on the fly while it does the compile job. Then you're producing actual code, right? When the call shows up. And one thing we've emphasized here, I think, when passing a class object to a function template, you got to make sure that all the operators used in the function template are actually defined or overloaded in the class definition. And our example there is if the square template function uses the asterisk multiplier, then that'll work with any incoming parameter that's overloaded operator times. So again, our square function will work with integers, chars, doubles, right? You can multiply any of those things. It will not work with a string, C++ string, because they didn't overload operator times. And it would work with feet inches, assuming we go in and we add operator multiply, as we were asked to do in one of the challenges in chapter 14. So if there's an operator multiply in the function, you got to have overloaded operator multiply in the object. And as long as that's the case, that function's happy to work on any type you send in. Really powerful. Okay, so now the question is, well, how do I develop this, right? If this is such a neat technique, how do I actually build one of these things? So templates are often appropriate for multiple functions that perform the same task, but basically with different parameter types. So if you've looked at any example in the past where we talked about overloading functions or maybe overloaded constructors, and it's more or less the same job just with different types, then that's a good option, a good place for where you could step in and use a function template to cut down on your coding time. And again, squaring's a pretty good example, right? You should be able to square integers or doubles or floats or a bunch of stuff like that. Any kind of measurement, pretty good example of that. I think there's another example in the book of a swap operation. Like you need to swap two variables. Happens in a lot of our sorting code quite a bit, actually. You ought to be able to swap two integers or two floats or two doubles or two strings or 2 feet inches or really two anything. So that right there is a really excellent example of you ought to use a function template for a swap two things function. That ought to work on any data type, frankly. So it's a good idea. Here's what I usually do when I'm building function templates is develop your function using standard data types first, right? Like ints. So I usually try to do my job and just make a function that works with integers and returns an integer, right? Test that, just make sure that that's working to begin with. Then once I'm happy with that, then I convert it to a template. I add the template prefix, the template bracket class T part, right? And then I convert all the data type names in the function to that abstract type parameter. So where I used to have integers, I turn them all into type T's. Okay, and hopefully that'll work with anything. And that's what I usually do is start off with like a normal function, just working on integers, then convert it to a function template like this. I think that's a good way to go about it. Okay, so hopefully that's a pretty good preview of function templates working with abstract data coming in. You don't even know what type of data is coming into the function, but as long as the operations sync up, it'll work properly, and the C++ compiler will be able to make sense of that. So this is the lab I would want to do with my students when we get together in person is in chapter 16. I'd actually look at one of the programming challenges here. Programming challenge 16.3 is the minimum maximum templates. So it's asking us to write a template function that computes the minimum of 2 parameters, and then another template function that computes the maximum of 2 incoming parameters. And so basically, if you think about it, that's a job that you want to do a lot, frankly, and it should work on any type of data that you can compare. So as long as you've got relational operators defined to determine whether one thing is bigger than another or not, you ought to be able to find the minimum or maximum of 2 such parameters. So, hopefully that's clear and obvious. Sometimes my students and I need to go look up the mathematical definition of the minimum function because that's exactly what we're coding up right now. And I would want to test our functions with at least 3 different data types. So this ought to work for 2 integers. This ought to work for 2 doubles. You should be able to compare 2 strings for dictionary order. We've done that before. You should be able to compare 2 feet inches objects and determine which of those 2 things is larger or smaller. And fortunately, if you look at feet inches version 5, the last version of it back in chapter 14, they did overload the relational operators, lesser or greater or equal to. So our functions should totally be able to work with feet inches objects, just like everything else, which is great. Okay, so that's a pretty good lab. Maybe you can see how that's going to work and just do it on your own, even if you don't have the book or something like that. That's actually a really good exercise to get started with function templates and more generally abstract data types. So when we come back next time, what a great technique this is. We're going to build out a little bit more because not only can you make template versions of individual functions, you can make templates for entire classes where the member data for the entire class is all an abstract data type T, and all the functions, suddenly all the public functions and all the private functions are now working on abstract data, abstract incoming parameters, abstract return values, and the whole class turns into this, and that's very, very powerful. And we'll also be talking about the standard template library that provides a whole lot of template classes just like that anytime you've got a C++ compiler. So hopefully that sounds interesting. Very, very powerful. We'll talk more about that all through the rest of this part of the course, the next several videos. So I hope you join me for that, and I'll see you then.